Hi gentlemen, these are your notes for Unit 2, Day 1 of Calculus. If you would like to see the warm-up, the homework questions we covered in class today, or the review problem, just look at the finished notes from today's module. So today we're going to begin our new unit on derivatives. So today we're going to be able to calculate the derivative, which is the slope of a function at a certain point using the difference quotient. And we did that at the end of the last unit. And we're going to be able to make conjectures about the relationship between a derivative and its original function. So if you're looking at its original function, what can you say about its derivative at different points? So the equation of a secant line, we talked about this at some point in some of our notes. So if we have some sort of function like this, and we wanted to find the slope of the function, or the slope of a secant line, we're trying to find the slope of the line that passes through two different points on the function. So this would be called the secant line. And it would go from 1, 2, 3, 4, 5, 6, from -6 to -2 on the x-axis. So it passes through the points -6, x equals -6 and x equals -2 on my function. So to find the slope of the secant line, the slope of the secant line is the same thing as what we've been calling the average rate of change. So the slope of the secant line is the same thing as the average rate of change of a function. And how do we find the average rate of change of a function? It's f at b minus f at a over b minus a. So remember, it's just a slope, so it's the change in the y values over the change in the x values. So this right here would be the point -6, -2, and this would be the point 2, 3. So if I wanted to find the slope of that line, I would do the change in the y value, so I would find f at -2 minus f at -6 over -2 minus -6. So this would be 3 minus -2 over -2 minus -6, which would be 5 over 4. So if I look at this, I should have gone up 5 over 4. So that is the slope of the secant line. Now to write the equation of a line, we can just use point slope form. So y minus y1 equals m times x minus x1. So we can just use point slope form whenever it needs us to write the equation of a tangent line or of a secant line. So I'm going to use the point -2, 3, and I'm going to use the slope that I just found, the slope of the secant line, 5/4. So it'll be y minus 3 equals 5/4 times x plus 2. And that would be the equation of the secant line that on the interval -2 or -6 to -2 of our function. So how is the slope of a tangent line different? So let's just look at the function y equals x squared. So we've got, and let's say we want to find the slope of the tangent line somewhere like there. So if we wanted to find the slope of the tangent line, so let's say we have y equals x squared, and we want to do it at x equals 2. To find the equation of the tangent line, the first thing we need to do is find the slope of the tangent line. So the slope of the tangent line is what we called previously the instantaneous rate of change, or the instantaneous velocity. And in order to find the instantaneous rate of change, we found the f at x plus h minus f of x all over h, where h is getting really, really close to 0. So I would want to find it at f at 2.00001 minus f at 2, all over 2.0001 minus 2. One more 0. And if I do that, and I plug it in, so it'd be 2.00001 squared minus 2 squared all over 0.00001. And if I evaluate that out on my calculator, I should get really close to 4, if not 4. So now I want to find that's the slope of my tangent line. And now I want the point. Well, I know x is equal to 2. To find y, let's plug it back into the original function. And so my point on the original function would be the point 2, 4. So if I have the point 2, 4, and I have a slope of 4, then the equation for my tangent line will be y minus 4 equals 4 times x minus 2. And that would be this equation for the tangent line that would touch the function at x equals 2. So now, remember what we did towards the end of our last unit? We found the difference quotient. So the slope of a tangent line is going to equal the change in y over the change in x. But if we want it for the tangent line, it's going to be f at x plus h minus f at x all over h. And then we want the limit as h is getting closer and closer and closer to 0. So that's one way of looking at it. And then there's going to be a couple other ways of looking at it when we get to our notes in a little bit. So let's do f of x equals x squared. So we're going to do the slope of the tangent line of this using the difference quotient. So it's going to be the limit as h goes to 0 of f of x plus h minus f at x all over h. So if I plug in x plus h in for the x, I would get the limit as h goes to 0 of x plus h squared, and then minus f at x is just x squared, so minus x squared all over h. And then if I multiply this out, I would get x squared plus 2xh plus h squared minus x squared. So again, I'm taking x plus h squared, and I'm going to multiply it out. So that's x plus h times x plus h, so which is x squared plus xh plus xh plus h squared, which when you combine your like terms, you get x squared plus 2xh plus h squared. And then this is all going to be all over h. And now notice the x squareds cancel. So now I have the limit as h goes to 0 of 2xh plus h squared all over h. Notice I can factor out an h from the numerator, and I get 2x plus h, and I factor out the h in front. And now those h's on the top and the bottom can cancel. And so my new limit is going to be the limit as h goes to 0 of 2x plus h. Well, if I plug in 0 for my h, this is just going to be 2x. This is the slope of the tangent line anywhere on the graph of x squared. So if I wanted to find the slope of the tangent line at 2, so if I wanted to find it at x equals 2, the slope of the tangent line would be 2 times 2, which would be 4. If I wanted to find it at 6, I would plug in 6. If I wanted to find it at 12, I'd plug in 12. At negative a half, I'd plug in negative a half. All right, so let's look at one of these using the difference quotient to write the equation of a tangent line. So we need the limit as h goes to 0 of f of x plus h minus f of x all over h. And so if we did this, this would be the limit as h goes to 0. I'm going to take x plus h and plug it in. So it'd be 2 times x plus h minus 1. And then minus f of x. Well, f of x is 2x minus 1. Then all over h. If I distribute this, then I would get 2x plus 2h minus 1. Then distribute the negative, so minus 2x plus 1 all over h. The 2x's cancel and the 1's cancel. So I have the limit as h goes to 0 of 2h over h. Those h's will cancel, and so I'm just left with 2. So that means that the slope of my tangent line is 2. Well, if we graph this, we would have negative 1 and then up 2 over 2. If I wanted to find the slope of this line at the point 3, 5, well, the slope of that line should be 2 because it is a line. And so if I have, that's my slope of my tangent line, and then I want it to pass through the point 3, 5, this would be y minus 5 equals 2 times x minus 3. And that would be the equation of the tangent line at that point, which is also just going to be the equation of the line because it is a line. So if I distributed this out, I get 2x minus 6, add the 5 over, and you get y equals 2x minus 1, which is the same thing as the original function because since it's a line, the tangent line is just going to fall directly on it. Let's look at the next one. Write the equation of the tangent line for f of x equals x squared minus 4 at the point negative 3, negative 5. So this would be a happy parabola 4 down. It has x-intercepts at 2 and negative 2. So this would be my happy parabola. And then I want to find the equation of the tangent line at negative 3, 5. So I want to know what the equation for that tangent line would be. So we're going to use the difference quotient. The limit as h goes to 0 of f of x plus h minus f at x all over h. So I'm going to take x plus h and plug it into my function. So this would be x plus h squared minus 4. and then minus f of x. So that's x squared minus 4, then all over h. I'm going to multiply that out, and I get x squared plus 2xh plus h squared minus 4. And then I'm going to distribute that negative sign, so minus x squared plus 4, and then all over h. The x squareds are going to cancel, and the 4's are going to cancel. So now I have the limit as h goes to 0 of 2xh plus h squared all over h. I can factor out an h, and I have h times 2x plus h all over h. Those h's will cancel, and now I have the limit as h goes to 0 of 2x plus h. But if h is going to 0, I'm just left with 2x. So the slope of my tangent line anywhere is going to be 2x. So now if I want it at x equals negative 3 and y equals 5. So if I plug negative 3 in, 2 times negative 3 is going to be negative 6. So the slope of my tangent line is negative 6, and it passes through the point negative 3, 5. So my equation for my tangent line will be y minus 5 equals negative 6 times x plus 3. So that would be the equation for that brown tangent line. All right, so find the equation of the tangent line at the given point. F of x equals x squared plus 2x plus 1 at the point negative 3, 4. Why don't you pause the video and try this, and then you can check your work against the finished notes from class today. So the limit definition of the derivative and different notations. So this is the limit definition that we've been using. The limit is h goes to 0 of f of x f of x plus h minus f of x over h. But there's different ways of doing it. Another common one is the limit as x goes to a of f of x minus f of a over x minus a, or the limit of f of a plus h minus f of a over h. Those are two different ways of saying the same thing. So just be aware that all of those are talking about the slope of the tangent line. So all of these are finding the derivative or the slope of the tangent line or the instantaneous rate of change of the function. They're all finding the same thing. And then we have some notations for the derivative. So if f of x is your original function, f prime of x is the notation we use for the derivative of f of x. So we call that f prime of x. That's how we would read that out loud. That's one way of doing it. Or we could call it dy over dx. That's another way of doing the derivative. So that means the derivative of y over the derivative of x. And notice it's like your delta y over your delta x. That's what those d's are. They're like the placeholders for the delta. So it's delta y over delta x. So that's another way of doing derivatives. Or you can do the derivative of f of x. So instead of putting the y, you could put an f of x off to the side. You can also do y prime. All of those are different notations for the derivative, which is the slope of the tangent line or the instantaneous rate of change. But the most common ones we'll use are f prime of x and dy over dx. So when you see those, it's asking you to find a derivative. All right, so let's go ahead and do this one, finding a derivative using the limit process. So now we have an x cubed. So we have the limit as h goes to 0 of f of x plus h minus f of x all over h. So it's going to be the limit as h goes to 0 of 2 times x plus h cubed minus 4 times x plus h, and then minus f of x, so 2x cubed minus 4x all over h. So I'm going to take x plus h cubed and multiply it out. So it's x plus h times x plus h times x plus h. So I get x squared plus 2xh plus h squared times x plus h, which gives me x cubed plus x squared h plus 2x squared h plus 2xh squared plus xh squared plus h cubed. So I get the limit as h goes to 0, and then if I combine like terms, I get x cubed plus 3x squared h plus 3xh squared plus h cubed, and then I'm going to multiply all of that by that 2 out in front. So I'm going to get 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed. And then I'm going to distribute this. So minus 4x minus 4h. Then I'm going to distribute that negative, and I get negative 2x cubed plus 4x, then all over h. So I get my 2x cubes will cancel, and my 4x's will cancel. So now I have the limit as h goes to 0 of 6x squared h plus 6xh squared plus 2h cubed minus 4h all over h. Now notice all of those terms in the numerator have an h that I can factor out, so I'm going to factor out an h. And I get 6x squared plus 6xh plus 2h squared minus 4 all over h. So those h's on the top and the bottom will cancel now. So now I have the limit as h goes to 0 of 6x squared plus 6xh plus 2h squared minus 4. If I plug 0 in for the h's, those will go away, and I'm just going to be left with 6x squared minus 4. So that is going to be the slope of the tangent line for the original function, f of x equals 2x to the third minus 4x. This is the slope of the tangent line, or the derivative, anywhere. So if I wanted to find the slope of the tangent line at 2, I'd plug in 2. If I wanted to find it at -1, I'd plug in -1, and so on. All right. Ooh, this one's a little bit different. It is a rational function, so let's find the slope of this guy's tangent line. So the limit is h goes to 0 of f of x plus h minus f of x all over h. So this is going to be the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. All right, this is going to be one of the complex fraction ones that we did in our last unit, so we're going to need a common denominator. So my common denominator is going to be x times x plus h. So it's going to be the limit as h goes to 0. This needs to be multiplied by x. This needs to be multiplied by x plus h. And so I get x minus x plus h all over x times x plus h all over h. So if I simplify the numerator, I'd distribute here, and those x's would cancel, so I'd get negative h over x times x plus h all over h. I'm dividing by h, which is the same thing as multiplying by 1 over h, so it's going to be the limit as h goes to 0 of negative h times x plus h times 1 over h. Now notice those h's are going to cancel. So now I have the limit as h goes to 0 of -1 over x times x plus h. Well, if the h goes to 0, then I have x plus 0, so this is just going to be -1 over x squared. So the derivative of the tangent line of the original function 1 over x is going to be -1 over x squared. Okay, so that is finding derivatives using the limit definition. What about the relationship between f and f prime graphically? So the slope of the tangent line. Well, if I were to draw in a little tangent line right there, what would be true about the slope of the tangent line there? Well, the slope of the tangent line there would be negative. So if I wanted to graph it, it would exist down here, right? Because it'd be a negative value. So it could be like -1. So right there, the slope of the tangent line would be -1. So it could have a point right there. Well, what's the tangent line right here? What's the slope of the tangent line right at the vertex? What's the slope of that little tangent line that I made? Well, the slope of that line is 0. So at 0, 0, it has a slope of 0. What about if I wanted to make it right here? Well, that looks like it's going to have a positive slope, right? Because the tangent line's going up. It looks to have like a slope of 1. So right there, I should have a tangent line that has a slope of 1. And then if I connected those, that is the graph of the derivative. So if I had a parabola, the graph of its derivative is going to be a straight line. The slope of the tangent line at its vertex will be 0. The slope where it is decreasing will be negative, and the slope where it's increasing is going to be positive. So it's going to be a line that starts negative, because the slope's negative, and then here the slope's 0, and then afterwards the slope is positive, right? All of these tangent lines have positive slopes, and all of these tangent lines would have negative slopes. So let's look at another one. What I recommend doing first is finding all the peaks and valleys, because the slope there is going to be 0. So the derivative at the peaks and the valleys is going to be 0, right? If I put in a tangent line right here, or put a tangent line in here, or I put a tangent line in here, or here, or here, the slope of those lines, since they're horizontal lines, the slope is going to be 0. So the derivative is going to be 0 at those points. So I'm going to put in the dots there to show that the derivative would be 0 there. And then whenever your function is increasing, that means that the derivative is positive, right? You are having positive slopes. And whenever your original function is decreasing, when it's falling, all the tangent lines would have negative slopes. So that means that their values would be negative. So let's look. Initially, all of those values are positive. So for it to have positive values, you need to exist above the y-axis. And I know that it's eventually going to have to pass through this point, so it's going to be positive. So all of these values are positive. I know that they're going down, but they're still positive, right? They have like a positive value of 1, of 2, of 3. And then after that dot, all of the tangent lines after that are going to have negative slopes because the function is decreasing. To have negative slopes mean your values are negative, so they need to exist below the y-axis. So they're going to exist. And then I know that I have to pass through this point, so it's eventually going to have to come back up and pass through that point. And then after that 0, all of the slopes of this tangent, or these tangent lines, are positive. So since they're positive, they're going to have positive y values, so they'll exist above the y-axis. And then after that, all of the slopes have negative values, so they'd exist below the y-axis, but I know that it's going to have to pass through this point. And then again, they have positive values, so they'll exist above the y-axis, and then so on and so forth. So that would be the picture of the derivative of the blue graph would be that purple graph. So that would be the graph of the derivative of the original function. All right, go ahead and pause the video and see if you guys can graph the derivative of this polynomial function. So remember, do the peaks and valleys first, and then where the function is decreasing, the derivative would be negative, and where the function is increasing, the derivative would be positive. So pause the video and try this one. All right, so the derivative is 0 at the peaks and the valleys, so the derivative would be 0 here and here. Before that first 0, before this 0, the function is decreasing, so all of the tangent lines would have negative slopes. Since they have negative slopes, they'd exist below the y-axis because they're negative in value, so they'd exist down here. And then after that, my function, the purple function, is increasing, so that means all of the derivatives, the slopes, would be positive, so they would exist above the y-axis. But I know that it's going to have to pass through this point, so it's going to go up and come back down. And then after that, the function, the original function, is decreasing, so all of the slopes of the tangent lines would be negative, and so they would exist below the x-axis. So that pink parabola would be the graph of the derivative of the original purple function. Your homework is 2.1. Actually, it's not. It's going to be a worksheet. If you have